Hello everyone, and welcome to Night Cosmos Sleep. Some stories in the universe do not begin with life or with familiar beauty. They begin with violent events. And strangely, it is sometimes from moments that seem to bring only destruction that the universe creates a new balance. Tonight, we will step into one of the greatest mysteries in Earth's history, how the moon was truly born. This is not only the story of a celestial body appearing beside our planet, it is also a scientific journey preserved in rocks, in orbits, in the movement of the oceans, and in the slow rotation of Earth. This journey takes us back more than 4 billion years, to a time when Earth had not yet become stable and the solar system was still filled with chaos. A violent collision changed the planet and tore away part of its material, yet at the same time, it created a companion called the Moon, which would remain beside Earth for billions of years afterward. Together, we will follow each trace left behind by time, so we can understand why the Moon is more than a body orbiting Earth. It is also a gentle memory preserved from one of the most violent events in the youth of our planet. Among the materials brought back from the Moon were pieces of rock so small that, if placed in the palm of a hand, they would appear almost completely ordinary. They do not glow or sparkle, and they do not possess the kind of beauty that immediately inspires wonder. Some are simply pale gray, with rough surfaces and uneven broken edges, resembling stones that have rested undisturbed in dust for a very long time. Yet those quiet fragments of rock transform the way humanity understands the Moon. They are not ordinary stones. They once rested on another world, a place where the traces of time have not been erased as thoroughly as they have on Earth. On our planet, rain, wind, oceans, volcanoes, and movements deep within the ground are constantly reshaping the surface. Ancient rocks are worn away, buried, heated again, and eventually turned into parts of newer layers of material. Earth is therefore always active and changing, but that same activity makes it difficult for the planet to preserve clear evidence from the earliest periods of its own history. The Moon is different. Its surface is quieter, drier, and less frequently disturbed. Impact craters can remain visible for immense spans of time. The gray dust and broken rocks covering the surface still preserve many clues from the youth of the solar system. So, when scientists study a lunar rock sample, they are not only learning about a distant celestial body, they are also looking into a part of the past that Earth no longer preserves clearly on its own surface. During the historic missions that carried human beings to the Moon between 1969 and 1972, astronauts brought approximately 382 kilograms of rocks, dust, and drilled core samples back to Earth. That amount is very small compared with an entire world, but for science, it represents an extraordinarily valuable archive. Before then, people could only observe the Moon from a distance, photograph its surface, measure its orbit, and develop theories about its origin. Once actual samples were returned, the question of the Moon's formation no longer belonged only to speculation. It could begin to be tested using material from the Moon itself. A small piece of rock cannot speak, but it still preserves the past in its own way. Within it are mineral grains, chemical elements, and traces of intense heating and cooling from an unimaginably distant time. Each small sign is like a line of notes in an ancient record. The record is incomplete and difficult to read at first, but it gives humanity enough information to begin following the trail. From these samples, a great question gradually emerged. How did the Moon truly form? Before these materials became available, several different explanations had been proposed. Some researchers thought the Moon might once have been an object wandering through space before being captured by Earth's gravity. Others suggested that Earth and the Moon formed beside each other from the same original material in the early solar system. Another idea proposed that the Moon had once been part of Earth and was somehow separated from it in the distant past. All of these ideas attempted to answer the same question: why does Earth have such a large companion? But as lunar rocks were studied more carefully, the story became more complicated and more fascinating. One of the first things to draw scientists' attention was how closely lunar rocks resembled rocks from Earth. This similarity was not found in their color or outward appearance. It existed deep within their material composition. In simple terms, every celestial body tends to leave a distinctive signature within its rocks, almost like a fingerprint. And when those signatures were compared, Earth and the Moon appeared surprisingly similar. If the Moon were simply a foreign object captured by Earth, this resemblance would be very difficult to explain. If it had formed completely independently, the same question would remain. Why would its rocks carry so many familiar signs shared with our planet? Yet the Moon is not merely a smaller copy of Earth, it is drier. It lacks many substances that are easily lost at high temperatures. Its iron core is much smaller than Earth's, and several lines of evidence suggest that the young Moon may once have been extremely hot enough for a large portion of its material to exist in a molten state. This combination of similarity and difference opened the way to a more powerful explanation. Perhaps the Moon was not born peacefully. Perhaps its beginning lay in an enormous event that occurred when Earth was still young and the solar system had not yet settled into the stability we know today. According to the hypothesis supported by many scientists, a large object in the early solar system collided with Earth. This object is commonly called Theia, and in many models, it was approximately the size of Mars. The collision may have melted and mixed material from both the young Earth and the incoming body, while throwing part of that material into the space surrounding the planet. From this hot and chaotic cloud of debris, the Moon gradually formed. What makes the story remarkable is that no one witnessed that moment. There are no actual images of the collision. No record survives from more than 4 billion years ago. All that remains are clues, lunar rocks, the Moon's motion around Earth, its material composition, and scientific models reconstructed much later. A small sample preserved inside a protective container therefore became the starting point of an enormous story. It does not reveal the entire past at once. It preserves only signs. Human beings must read those signs slowly, compare them with what is known about Earth, and gradually assemble a picture blurred by time. The more closely we examine those rocks, the more clearly we see that the Moon is not merely a celestial body orbiting Earth. It may be the surviving result of an event that transformed our planet during its earliest history. Behind the quiet appearance of lunar stone are traces of extreme heat, molten material, and an age when Earth had not yet taken on the familiar form we know today. The samples brought back from the Moon more than half a century ago are still being studied. As technology becomes more precise, the same small piece of rock can reveal details that earlier generations were unable to detect. A new measurement may help establish the Moon's age more accurately. A new analysis may reveal more about how it cooled. A tiny signature within the rock's composition may cause scientists to adjust the way they imagine the impact that created it. The science of the Moon is therefore not a finished story. It is still being read, beginning with small samples that contain evidence from an immense span of time. Within a gray fragment of rock lies the memory of a younger and more violent solar system, when planets were still colliding as they struggled to become the worlds they are today. That small piece of rock does not need an extraordinary appearance to be important. What makes it remarkable is the immense journey it has traveled and the ancient traces it still preserves within. From something that seems completely silent, humanity has begun following the story of an age far more violent than the stable world we know today. From a small rock brought back from the Moon, the story begins to open far beyond its quiet gray surface. The traces preserved inside that rock do not lead us only to the Moon. They also carry us back to a time when Earth was still very young, before the planet had its familiar blue color, before stable oceans had formed, and before it became the peaceful home of life that we know today. To understand how a collision could have created the Moon, we first need to return to a time when Earth was still unfinished. It was a world very different from the one we live on now, hotter, more violent, and still growing within a solar system filled with wandering fragments of matter. About 4.6 billion years ago, the solar system began forming from an enormous cloud of gas and dust. At the center, most of the material gathered together to create the Sunday. Around it, tiny grains of dust and pieces of rock continued moving, colliding, sticking together, and gradually forming larger bodies. Over immense spans of time, planets began to emerge from this scattered material. Earth formed not long afterward, but the newly formed Earth did not resemble a complete planet. It did not yet have a stable surface, blue oceans, clearly defined continents, or life. When we speak of the early Earth, we mean Earth during its youth, when everything was still changing and the planet had not yet taken on the familiar form it has today. The surface of Earth may have been extremely hot. Large regions may still have been molten or repeatedly reheated by impacts from space. Smaller bodies continued striking the planet, adding new material while also generating heat and breaking apart the surface layers that had only recently formed. Earth did not grow gently. It grew through collisions, heat, and the mixing of rock, metal, and leftover material from the beginning of the solar system. Today, we are familiar with Earth as a blue planet covered by oceans, white clouds, and stable land. But that image did not yet exist during its earliest history. The planet was too young for calm conditions. Its crust, if it had begun forming in some places, could still be shattered by new impacts. Earth's interior held an immense amount of heat. Heavy materials such as iron gradually sank deeper, helping form the planetary core, while lighter material remained nearer the outside and slowly became the foundation of the future crust. The formation of a planet is not a simple moment. It is a long process in which material is continuously gathered, separated, heated, and cooled. These events may sound chaotic, but this is how worlds are created. In the young solar system, collisions were not unusual. They were a natural part of planetary formation. Many wandering fragments of material still surrounded Earth. Some were only small blocks of rock. Others were much larger, resembling incomplete planets. They traveled along orbits that had not yet become fully stable. Some objects were pulled into the Sunday, others were pushed farther away. Some collided with the planets that were still forming. Every encounter could change the direction, speed, or even the fate of an entire world. Within this environment, the early Earth was not a quiet place waiting for life to appear. It was a planet being strongly shaped by everything around it. Whenever a large object struck, the energy of the impact could be transformed into enormous heat. Rock could crack, melt, and be thrown away from the surface. If the collision was powerful enough, some material could even be launched high above the planet and into the surrounding space. This is extremely important to the story of the Moon. If the Moon truly formed from a giant collision, that event did not occur beside an Earth as stable as the one we know today. It happened during a period when enormous impacts were still capable of reshaping planets. Earth was still hot, still easily transformed, and still in the process of becoming itself. We can imagine the young Earth as a world that had not yet had time to cool completely. Its surface was not peaceful. The space around it had not yet been cleared of leftover objects. The planet continued gathering material, enduring new collisions, and slowly reorganizing its interior. The regions that would later become the core, mantle, and crust were still gradually settling into place. Everything was moving toward order, but the path toward that order was far from gentle. At that time, life was still far in the future. There were no forests, no living creatures, and none of the familiar oceans moving with the tides. Earth was not yet the home of life. It was a young planet passing through the most difficult stage of its formation. Yet within this violent period, the basic conditions for the future were also slowly being prepared. The planet needed time to cool, its material needed time to stabilize, its internal layers needed to separate more clearly, and it needed an extremely long history before it could become the blue world we know today. This story also reveals something quiet but profound. Stability does not always exist from the beginning. It is formed through many changes. Earth was not born as a gentle planet. It was once hot, rough, incomplete, and shaped by both the objects around it and the heat within it. Over time, collisions and repeated cycles of melting and cooling helped create the final form of the planet. And among all those events, there may have been one greater than the rest. A massive body, not merely a small meteorite, but something closer to a young world was traveling along an orbit that would bring it near Earth. In many scientific models, this object is imagined as being roughly the size of Mars. It was large enough that, if it struck Earth, the result would not be only a crater or a wound on the surface. It could change Earth's rotation, melt enormous amounts of material, and throw part of the planet's hot rock into the space surrounding it. For now, we do not need to enter the moment of impact itself. What matters first is to feel the kind of world in which such an event could occur. An Earth far younger than today, without its blue color, without life, and without the moon beside it. A solar system still filled with chaos, where objects large and small continued searching for stable paths. A time when a single encounter at the wrong angle could change the future of an entire planet. During that age, Earth was not alone. Another world may already have been moving along an orbit that would cross its fate. When Earth was still very young, our planet was not alone. Many objects were still moving around it on orbits that had not yet become fully stable. Some were small fragments of rock, some were larger bodies of material, and some were young worlds still in the process of forming. The solar system had not yet become as orderly as the familiar arrangement we see today, with planets following relatively stable paths around the Sunday. It was a place filled with motion, collisions, and futures that had not yet been decided. Within that environment, there may once have been an extremely large object, far larger than an ordinary meteorite. It was not simply a piece of rock traveling through space. It may have been a planetary embryo, an object on its way toward becoming a planet, though not certain to survive until the end of the solar system's formation. In simple terms, a planetary embryo was like an unfinished world. It was already large enough to have gravity of its own and to draw in additional material from around it, but it did not yet have a guaranteed or stable future. During the early solar system, many planetary embryos like this may have existed. Some continued to grow, gathering more material until they became the planets we know today. Others were absorbed by larger planets. Some were thrown into unfamiliar orbits, and some disappeared in powerful collisions, leaving their material behind within other worlds. The object that entered Earth's story may have belonged to this final group. Today, we cannot observe it as a separate planet. There is no point of light in the sky that can be identified as the direct remains of that world. There is no surface to photograph, no present orbit to measure, and no rock sample that has been confirmed with certainty as an intact surviving piece of it. If it once existed, its individual form vanished long ago during an event that occurred while Earth itself was still forming. But the disappearance of a world does not mean that it left nothing behind. In many scientific models, this mysterious object is often imagined as being roughly the size of Mars. This is not an absolutely certain measurement, because no one can directly measure an object that no longer exists. But the comparison helps us understand its scale. Mars is smaller than Earth, yet it is still a true planet, thousands of kilometers across, with a vast surface and enough mass to exist as a world in its own right. So, if the object that struck Earth was somewhere near that size, the collision could not have been a minor event. An ordinary meteorite can create a crater. A larger object can melt a broad region of the surface, but a planetary embryo nearly the size of Mars, striking the early Earth, could transform the entire planet. It could heat vast amounts of material, melt rock, disturb the outer layers, and launch an enormous quantity of debris into the space surrounding Earth. This makes the lost object a remarkable figure in the story of the moon. It no longer exists for us to see, but if the giant impact hypothesis is correct, its disappearance was closely connected to the moon's birth. One world may have lost its separate form, while a new celestial body began forming from the material thrown outward after the collision. We should not imagine this object as a deliberate destroyer rushing toward Earth. The universe does not act with intention in that way. It did not choose to strike our planet. It simply moved along its orbit, influenced by the gravity of the Sun, Earth, and other bodies in the young solar system. In an environment that was still chaotic, even a small change in its path could lead to an extremely close encounter. And when two massive bodies pass too close to one another, gravity can turn that approach into a collision that can no longer be avoided. Before the collision, that object may have orbited the Sun in a region of space close to Earth. It did not necessarily come from somewhere extremely distant. It may have belonged to the same part of the solar system where the rocky planets were forming. This is important because, if the object formed near Earth, its material may not have been very different from the material of our own planet. This is one reason scientists are so interested in where it came from. If the Moon is connected to that lost body, then the similarities between lunar rocks and rocks from Earth may be understood in several different ways. After the collision, the object may no longer have retained its original form. Some of its material may have merged with Earth. Another portion may have been thrown outward together with material from Earth's outer layers. That ejected debris could have orbited the planet, collided with itself, gradually gathered together, and helped form the Moon. Still more material may have been scattered into space or later fallen back to Earth. So when we say that this world disappeared, we do not mean that all of its material ceased to exist. It vanished as a separate planet, but parts of it may have survived in other forms. Some of its material may remain deep inside Earth. Traces of it may exist within the Moon. The mixing of these two young worlds may have created the features that make the Moon both closely related to Earth and marked by an extremely hot and violent past. This is where the story becomes deeper. The Moon is not simply a mass of rock that appeared beside Earth. It may be the result of an encounter between two unfinished worlds. One of them continued to exist and gradually became the blue planet we call home. The other lost its separate form, but left its material behind within a new story. From the collision, the heat, and the material that was mixed together and thrown outward, another celestial body gained the opportunity to form. None of this is based on imagination alone. Scientists cannot travel back more than 4 billion years to witness the collision, nor do they possess a map showing the exact location of the lost object. What remains are indirect clues: lunar rocks, their composition, the similarities between the Moon and Earth, the Moon's motion around our planet, and computer simulations constructed using the laws of physics. A gentle way to understand this is to think of footprints in sand. Even if we did not see the person who walked there, we could still know that someone had passed through. A footprint is not the person, but it is evidence that something happened. The same may be true of this lost object. We cannot see it in the solar system today, but we may be able to see the influence it left behind in the Earth-Moon system. That evidence is not preserved in only one place. It may exist within lunar rocks, whose material composition points toward a past deeply connected with Earth. It may be found in the Moon's orbit and in the way this body has remained beside our planet for billions of years. It may also be found in the question of why Earth has such a large satellite compared with its own size. When all these clues are placed together, the image of a large vanished object becomes more convincing. Even so, caution remains necessary. This object is part of a scientific model, not a planet that has been directly observed. Describing it as roughly the size of Mars is a common way to picture it, but it is not an absolutely fixed measurement. The way it struck Earth, its speed, the angle of approach, and the amount of material thrown outward after the impact are still being studied and adjusted within different models. This uncertainty does not make the story less compelling. Instead, it brings the story closer to the way science truly works. Science does not always begin with a complete answer. Often, it begins with small traces, unanswered questions, and models that must be tested many times. From there, the larger picture gradually becomes clearer, one layer at a time. The lost object is like a character who never appears directly, yet whose absence gives the story greater meaning. Without a large body striking the early Earth, it becomes difficult to explain why the moon has the features we observe today. Without an event hot and powerful enough, the signs preserved in lunar rocks become harder to understand. And without material mixing on a planetary scale, the close relationship between Earth and the moon would be missing an important piece. We can imagine that world as a planet that never had the chance to receive a name in the sky we know today. It once existed within a young solar system, traveled among unstable orbits, and carried the possibility of becoming an independent world. But its fate may have changed when its path brought it too close to Earth. From that moment onward, its story was no longer separate. It became part of the story of our planet. For this reason, if we view the moon's origin through the giant impact hypothesis, its formation was not only the appearance of a new celestial body, it was also the ending of another world. That world lost its individual form, but it may not have disappeared completely. Its material may have become part of Earth, part of the moon, or part of the debris scattered after the impact. Within the immense timeline of the solar system, events like this may sound violent, but they are also part of the process through which planets form. Worlds are not always created peacefully. Often, they emerge from collisions, mixing, loss, and reconstruction. A planet may grow by absorbing another body. A moon may form from the debris of a gigantic event, and a vanished world may leave traces inside a world that still remains. Before the moon existed, a large object may have passed too close to Earth. It left no separate planet for us to observe. It no longer appears on any map of the solar system as an independent world. Yet traces of it may still remain in rocks, in orbital motion, in the strange similarities between the moon and Earth, and in the very existence of the moon itself. That world left no planet behind for us to see. It left only traces in stone, in orbit, and in the moon's existence. The moment that changed Earth forever occurred during an age when no one was there to witness it. Our planet was still very young. Life had not yet appeared, and the moon did not yet exist in orbit. Earth's surface was not as stable as it is today. Many regions were still hot, easily disrupted, and capable of being melted again by impacts from space. The early solar system was not yet the orderly system we know now, with planets following clearly established orbits. Many objects, large and small, were still moving around the sun, pulling one another away from their paths, colliding, and changing one another's fates through violent encounters. If the collision that created the moon truly occurred, it left behind no film for humanity to watch. No living creature stood on Earth's surface to remember that moment. There were no cameras, no written records, and not yet the familiar atmosphere that carries sound across the world as it does on Earth today. The event belongs to a past so deep that we can approach it only through the traces it left behind. Those traces became the beginning of a very slow scientific investigation, in which every clue is small, yet together they suggest an event greater than anything Earth would experience afterward. A lunar rock may preserve evidence of extremely high temperatures. Its chemical composition may reveal the moon's close connection to Earth. The moon's orbit suggests that it is not simply a small object that happened to pass by and was then captured by our planet. Earth's rotation must also be considered, because an impact large enough to create the moon could have left lasting effects on the way our planet spins and on the way the moon travels with it. No single piece of evidence tells the entire story, but rocks, orbital motion, material composition, planetary rotation, and computer simulations are like scattered files from an event that had no witnesses. From these clues, the giant impact hypothesis became an important explanation for the moon's origin. According to this idea, a large object may have collided with the early Earth. That body no longer exists as a separate planet for us to observe, but in many models, it is described as a planetary embryo roughly the size of Mars. This was not a small meteorite falling onto the surface and leaving behind a crater. A body nearly the size of Mars would have been a young world carrying enormous mass and tremendous energy as it moved through space. If such an object struck Earth, the effects would not have been limited to the surface. It could have melted rock, mixed material together, altered the planet's motion, and thrown a vast amount of matter away from Earth. An important part of the story is how the collision may have happened. In many models, the lost object did not strike directly into the center of Earth. Instead, it approached at an angle. In simple terms, an oblique impact occurs when two bodies do not collide head-on, but strike off-center, more like a powerful sweeping blow across their outer layers than a direct hit through the middle. This difference matters. A head-on collision might force most of the heated material deep into Earth. An angled impact, however, could tear material away from the outer layers of both worlds, throw it high above the surface, mix material from Earth with material from the lost body, and create a region of hot rock, dust, and vaporized stone orbiting the planet. That ejected material is the key to the story of the Moon. Before the moment of impact, the two massive bodies may have approached one another in the absolute silence of space. In a vacuum, sound does not travel as it does through air. A planetary collision can release an unimaginable amount of energy, yet from a distance, there would be no thunderous roar like the ones heard in movies. Perhaps the most unsettling part of that moment was not the sound, but the silence. There were only motion, mass, velocity, and gravity working without a voice. Even from a great distance, Earth and the approaching body may have begun gently altering one another's paths. Gravity shifted their orbits little by little, gradually narrowing the distance between them. And within a young solar system, even a small change could bring two worlds into an encounter that could no longer be avoided. As the distance between them became dangerously small, gravity was no longer only a subtle influence. The lost body began to fall more deeply into Earth's gravitational reach, while our planet was also affected by the mass of the approaching world. Both were orbiting the sun, both carried enormous energy, and both were moving toward a point beyond which neither would remain unchanged. Then the surfaces of the two worlds touched. This was nothing like a stone falling onto the ground. The scale was vastly greater. When a planetary embryo, nearly the size of Mars, struck the early Earth, the energy released may have been enough to melt rock across enormous regions, tear open the planet's outer layers, compress and heat material, and launch it outward at tremendous speed. In that violent moment, the boundary between the two worlds may have disappeared. Material from Earth mixed with material from the mysterious planetary embryo. Solid rock became magma, which is rock heated into a molten state. In even hotter regions, some of the material may have vaporized into rock vapor. What had once been the surface was broken apart, while the outer layers of both bodies were rearranged in an entirely new way. Earth did not merely receive a wound. It was transformed. The collision may have affected its rotation, its temperature, its outer layers, and even the region of space immediately surrounding it. From a young planet that was already unstable, Earth entered an even more violent state, hotter, more deeply mixed, and surrounded by material that had just been thrown away from its own body. The impact was therefore not only an act of destruction. In the story of the Moon, it was also a stage of preparation. Without enough material being launched into orbit, the Moon could not easily have formed in the way proposed by the giant impact hypothesis. The field of debris left after the collision became the Moon's earliest raw material, though it did not yet resemble a complete celestial body. The space around Earth may have been filled with a hot, chaotic mixture of molten rock, dust, rock vapor, and fragments of many sizes moving at different speeds. Some pieces lost their orbits and fell back to the surface. Others may have traveled farther away. The material that remained held by Earth's gravity continued circling the planet, colliding, breaking apart, sticking together, and gradually forming larger bodies. The moon did not need to appear fully formed in the first instant. Before becoming a clearly defined world, it may have begun as a hot and disordered region of material where countless fragments repeatedly encountered one another. Over time, gravity gathered them together. Smaller collisions allowed larger masses to develop. The original debris field gradually became less chaotic, and a new celestial body began separating itself from the surrounding material. What began as a violent collision slowly became a process of construction. From shattered matter, a new companion for Earth gained the opportunity to be born. What makes this story resemble a scientific investigation is that humanity cannot look directly into the past. Scientists must test it using many different forms of evidence. Lunar samples provide clues about temperature and material composition. Chemical comparisons between the Moon and Earth help raise questions about their shared origin. The Moon's orbit shows that it has remained connected to Earth within a distinctive system of motion. Earth's rotation must also agree with the effects that a giant impact could have left behind. No single clue is enough to prove the entire story, but when several lines of research point toward the same possibility, the giant impact hypothesis becomes more strongly supported. To test those possibilities, scientists use computer simulations. Put simply, a simulation uses the laws of physics to reconstruct an event that cannot be observed directly. Researchers change the size of the impactor, its speed, its angle of approach, and the condition of the early Earth, then examine whether the result produces a system resembling the Earth and Moon we see today. Some simulations place too little material around Earth, leaving too little to form the Moon. Others send too much material outward or cause most of the debris to fall back to the planet too quickly. The more convincing models must explain several things at once. Earth must survive the collision. Enough material must reach orbit. The Moon must be able to form from that debris, and its composition must remain closely connected to that of our planet. This process of testing gives the investigation its distinctive scientific character. Lunar rocks raise questions. The Moon's orbit provides another perspective. Chemical composition helps eliminate scenarios that do not fit. Computer simulations allow researchers to test possibilities that could never be recreated in real life. Each field of study is like an indirect witness. None can describe the entire event, but each contributes something to the larger picture. Many details remain uncertain, including the exact size of the lost body, its speed when it reached Earth, the angle of impact, and the quantity of material launched outward. Science does not treat this ancient event as a story that has been closed with absolute certainty. It is more like an old case file being reopened and examined with increasingly precise tools. Even so, the idea of an oblique impact remains especially powerful. It helps explain how material could have been thrown into orbit instead of simply being driven deep into Earth. It also shows how the Moon could have formed from matter closely related to our planet. More importantly, it turns the Moon's birth into the result of a specific physical process involving motion, gravity, energy, heat, and the rearrangement of matter after a collision. Although no one witnessed the event, matter preserves what happened in its own way. Rocks retain evidence of temperature. Orbits preserve evidence of motion. Chemical composition carries signs of origin. And scientific models help humanity assemble those traces into a coherent story. Before the event, Earth was a young planet growing within chaos. Afterward, it was no longer the same. Part of its material had been thrown outward. The lost body no longer retained a separate form. The region around Earth now contained the raw material for a new celestial body, and from that destruction, the story of the Moon entered its next stage. No sound from that moment remains. No direct image survives for humanity to examine. But traces of the collision may still exist within lunar rocks, within the Moon's quiet orbit around Earth, and within the models science uses to reconstruct an event no one ever saw. After that moment, Earth had not merely been struck. It had been remade. After that collision, Earth did not simply carry another wound on its surface. On a planetary scale, a major impact is nothing like the kinds of collisions we imagine in everyday life. When an enormous body struck the early Earth at very high speed, the energy of that motion did not simply disappear. It was transformed into heat, pressure, fracture, crushing, and the mixing of material. In that moment, even the things that seem hardest and most permanent could lose their familiar form. Rock, which we usually think of as solid, cold, heavy, and nearly motionless, could be transformed completely. In everyday life, rock gives us a strong sense of stability. A boulder can remain outside through years of sunlight and rain. A mountain of stone can stand for so long that we almost forget it is still matter, and that it too can change if placed under sufficiently extreme conditions. But that durability is true only within the familiar environment of present-day Earth. When temperatures rise high enough and pressure becomes overwhelming, rock no longer behaves like an ordinary solid. If heated sufficiently, it can melt into magma, which is molten rock. If the temperature becomes even higher, part of the material within the rock can even enter a vapor state. This may sound strange because, in everyday experience, we are used to seeing water evaporate, while rock seems never to do so. Water needs only to be heated on a stove before it can become vapor. Rock is very different. It requires far higher temperatures to melt, and even more extreme conditions for part of its material to vaporize. But in a collision between planetary-scale bodies, the released energy can be so immense that these difficult-to-imagine transformations become possible. Rock is compressed, subjected to intense friction, and heated in an extremely short period of time until it can no longer remain in its original solid state. So if the impact that created the moon truly occurred, it was not only a violent spectacle, it was also a process that transformed matter. The outer rocky layers of the early Earth may have been heated until they melted. Some material from the impacting body may have mixed into them. In the hottest regions, rock may not only have melted, but also become rock vapor. This was not gentle water vapor rising through the air as in everyday life. It was rocky material being forced into an extreme state where temperatures were high enough to break the familiar limits of matter. After the impact, the early Earth may have entered a period of extraordinary heat. Its surface was renewed, its outer layers were disturbed, and material from the two young worlds mixed together in molten or nearly vaporized form. Some of that matter remained within Earth, while another portion was thrown into the space around the planet. This surrounding material did not begin as cold stones floating quietly in orbit. It may have been an intensely hot mixture of molten rock, dust, rock vapor, and fragments of material gradually cooling after the collision. That extreme heat helps explain an important clue found in lunar rocks: the depletion of certain volatile substances. In simple terms, volatile substances are materials that are easily lost when exposed to high temperatures. Water is the most familiar example because it evaporates far more easily than rock. But in planetary science, the idea of volatility includes more than water. It also refers to components within matter that tend to separate, escape, or become difficult to retain when the environment grows extremely hot. When scientists studied lunar rocks, they found that the moon is drier than Earth and poorer in certain volatile substances. This does not mean that everything on the moon was burned away, nor does it serve as the only evidence for its origin. But the depletion fits well with the idea that the material forming the moon passed through a period of extreme heat. If that matter was intensely heated after the impact, the more easily lost components could have separated or escaped, while more resistant materials remained and gradually became rock. Seen this way, the moon may still carry evidence of a violently hot beginning. The quiet surface we see today does not immediately reveal this history. Its gray regions, craters, and dark plains appear cold, dry, and still. Yet within its rocks, there may remain signs of an entirely different age, when matter had not yet stabilized. Temperatures were still extremely high, and the body that would become the moon had not yet taken on a clear form. This is also why lunar samples are so valuable. A small stone does not only tell us about the moon's present surface, it can also suggest the physical conditions that existed when the moon was first forming. If the rock shows evidence of melting, the loss of volatile substances, or a composition closely related to Earth's, those features become clues that help humanity reconstruct the past. The impact then becomes more than an image created in a computer simulation. It begins to be tested against the surviving material itself. After the collision, the region around Earth may have been filled with a hot and chaotic cloud of matter. It was not yet a beautiful, thin, orderly ring like the familiar images of planetary rings. In the beginning, this region may have been thicker, more disordered, hotter, and changing far more rapidly. It contained hot rock, dust, rock vapor, droplets of molten material, and larger fragments still moving through space. Some matter fell back to Earth. Some may have traveled farther away. The portion held by Earth's gravity continued orbiting the planet. Over time, that material could not remain in its original chaotic state forever. It began to cool. Denser regions drew nearby matter inward. Small fragments collided, sometimes breaking apart and sometimes sticking together, gradually creating larger bodies. Temperature played a crucial role in this process. If the material remained too hot, many volatile components could continue escaping. As it cooled, new minerals could begin to form, and if Earth's gravity was strong enough to hold the material nearby, the debris field could remain around the planet rather than dispersing completely into space. Melting, then, was not only a sign of destruction. It also created the conditions needed for matter to mix and reorganize. When rock remains solid, different parts of the material preserve their own structures more clearly. But when rock melts, its components can blend, move, separate, or combine in new ways. The collision did not merely shatter matter. It created an environment in which material from two young worlds could mix together and later cool into new forms. This helps explain why the moon is both closely related to Earth and not completely identical to it. The similarity may come from material connected to our planet. The differences may have emerged from the extreme heat after the collision, when some volatile components were lost, and the remaining matter went through a process of reorganization. The moon is not a smaller copy of Earth. It has its own history, but that history may have begun with an event that happened very close to our planet. When we say that rock could vaporize, we do not need to imagine all the material turning into a thin gas-like steam. A more accurate picture is that, in the hottest regions of the collision, some matter entered a vapor state, while other portions melted, shattered into fragments, or cooled into droplets. The post-impact mixture was therefore extremely complex. It was not only rock, and it was not only vapor. It was a region containing matter in many different states, all controlled by heat, velocity, smaller collisions, and Earth's gravity. From this state, a hot ring of material may have begun forming around the planet. This ring did not necessarily resemble the thin, even, beautiful rings of Saturn. In its earliest stage, it may have looked more like a broad region of hot material in orbit than a fully formed ring. What mattered was that, after the collision, some of the material did not immediately fall back to Earth. Instead, it continued moving around the planet. That orbiting region became the place where the story of the moon entered its next stage. Scientists are deeply interested in this phase because it connects the impact itself to the moon's actual formation. If there had been a collision but no material remained around Earth, there would not have been enough raw material to create a large satellite. If matter stayed in orbit but could not gather together, the moon would also have struggled to form as it did. So after the moment when rock melted and vaporized, the next important question is how that hot orbiting material cooled, became less chaotic, and began to collect into larger bodies. Everything begins with something almost unbelievable when judged by ordinary experience. Rock, which seems so hard and permanent, may once have melted, vaporized, mixed together, and been thrown into space after a planetary collision. During that event, matter lost its familiar form, but it did not disappear from the story. It simply entered a different state, and from that altered state, new possibilities began to emerge. From material heated beyond recognition, a hot ring began to form around Earth. From material heated until it no longer retained any familiar form, a hot ring began to take shape around Earth. After the giant collision, not everything simply fell back onto the planet immediately. Some material remained within Earth. Some may have been thrown farther away, but another portion was launched high enough to continue moving around the planet. That material formed a hot, chaotic disk, the first place where the moon had a chance to be born. At that time, there was no clearly defined round body, no cold gray surface, and none of the familiar craters. There was only hot rock, dust, rock vapor, and fragments of many sizes orbiting an Earth that had just been remade by the impact. This ring of debris was not a stable structure. It had been born from heat, from the force of collision, from material torn away from Earth's outer layers, and from what remained of the lost body. In its earliest stage, the region surrounding the planet may have been extremely thick, hot, and uneven. In some places, matter was still molten. Elsewhere, part of the rock had been turned into vapor. Dust and larger fragments moved at different speeds. Everything was orbiting, but not as a single unified mass. Each portion followed its own path, colliding with others, being pulled off course, falling back, or remaining in orbit. It was a ring born from chaos, not from balance. To understand why some of that material could remain around Earth, it helps to think simply about an orbit. When an object is thrown upward from the surface, it will fall back if it is not moving fast enough. If it moves too quickly in the right direction, it may escape the strongest pull of the planet. But between those two possibilities lies a special state. The object continues falling toward Earth while also moving sideways fast enough to keep circling the planet without striking the surface. That is an orbit. After the collision, some of the hot rock and debris may have entered this state. It no longer rested on Earth, but it had not completely left Earth either. It became material orbiting the planet. Within that disk, the material was constantly changing. Fragments closer to Earth felt a stronger pull and may have fallen back more quickly. Pieces farther away had a better chance of remaining in orbit for longer, but if they traveled too far or moved at the wrong speed, they too could be lost from the original debris field. The ring was therefore not a quiet place after the impact. It was like a flowing region of hot material reorganizing itself, where every fragment passed through a kind of selection, which pieces would fall, which would escape, and which would remain long enough to take part in the moon's formation. Temperatures within the ring were still extremely high. Material thrown outward by a planetary collision could not cool immediately. Some fragments may still have been soft and molten. Other portions existed as dust or rock vapor. When pieces struck one another, the result was not always the same. If the collision was too violent, they could break into smaller fragments. If the speed and physical state were more favorable, they could stick together, merge, or form larger masses. In a region filled with hot rock and dust, every small collision helped change the shape of the ring. Some impacts spread the material farther apart, while others began bringing it together. This phase was crucial because it connected the collision itself with the moon's actual birth. If all the material had fallen back to Earth, there would not have been enough raw material outside the planet to create a large satellite. If the debris had been thrown too far away, it could not have become the moon either. What needed to happen was for some material to remain in orbit around Earth long enough to cool, collide, and accumulate. Accumulation simply means the process by which smaller pieces gather into larger bodies. At first, this process may have been weak and unstable. A newly formed mass could be shattered again by another collision. But if enough material remained close together, and if the differences in speed were not too great, larger bodies gradually gained a better chance of surviving. As a larger mass formed, its own gravity also became stronger. Gravity is the attractive force between objects that have mass. A single grain of dust has an extremely weak pull, almost insignificant on its own. But a larger body can begin drawing nearby fragments toward it. At first, this advantage is very small. Yet in a region filled with loose material, even a slight advantage can become a beginning. A larger mass attracts more debris and grows larger still. The process does not need to be loud. It unfolds quietly through individual collisions, repeated mergers, and moments when matter is retained instead of being thrown away. Not every part of the ring, however, was favorable for accumulation. Too close to Earth, the planet's gravitational pull was strong and uneven. The side of a forming body nearer Earth was pulled more strongly than the side farther away, which could stretch the body apart or prevent it from gathering into a large object. This is why position within the debris disk mattered so much. Material needed to remain close enough to stay in orbit around Earth, but far enough away to begin combining into larger masses. In such favorable regions, scattered fragments had a chance to move from chaos toward a more stable structure. The debris ring can be imagined as the moon's first violent cradle, but it was not a peaceful one. It was hot, disordered, filled with collisions, and constantly changing. What would later become the moon did not yet resemble a celestial body. It existed only as a possibility within molten rock, fine dust, rock vapor, and fragments orbiting Earth. From the outside, the region may have looked like wreckage left behind after a catastrophe. Yet within that chaos, the first conditions for formation were being prepared. Temperatures slowly declined. Matter collided again and again. Small bodies appeared and began to grow. The original disorder gradually gave way to a clearer process of accumulation. What makes this ring especially important is that it existed only as an intermediate stage. It was neither the final result of the impact nor the completed moon. It was a bridge between two states, from matter that had been broken apart to matter being reorganized. Within Earth's very long history, this period may have been brief compared with the billions of years that followed, but its role was immense. Without this hot region of orbiting material, the story of the moon would be missing its most important step. The place where the raw material was preserved, cooled, collided, and began gathering into a new world. No one ever saw this debris ring. There are no real images of it, and no direct trace remains completely unchanged from that earliest stage. But scientific models, the composition of lunar rocks, and the way the moon moves with Earth all make this phase necessary within the giant impact story. If the moon formed from material launched, it was a place where matter did not all fall back, did not disappear entirely into space, but remained long enough for a new process to begin. Seen from a wider perspective, the debris ring shows that the universe does not create only through peace. Sometimes a new structure begins with the remains of a violent event. A collision shattered the surface, melted rock, and threw material into space. Yet that same ejected material became the raw substance of another celestial body. Chaos did not last forever. As temperatures fell, as smaller collisions continued, and as gravity worked silently, scattered fragments began finding one another. From a hot disk of material surrounding Earth, the story of the moon entered a new stage. Within that ring, gravity began its quiet work, drawing the scattered fragments closer together. Within the hot ring surrounding Earth, gravity began pulling fragments of material closer together. Dust, molten rock, and bodies of many different sizes continued moving along separate orbits. Some fell back to the planet, while others were pushed farther away. But the fragments that remained continued to encounter one another. They collided, broke apart, stuck together, and gradually formed larger bodies. This process is called accretion. Put simply, accretion occurs when many small objects gather together to create a larger one. It is also how planets grew in the young solar system. Dust grains joined to form pieces of rock. Those pieces became larger bodies, and gravity continued drawing more material toward them. The moon may have formed through the same basic process, but from a dense disk of matter orbiting close to Earth. Not every collision within the debris disk helped the material grow. When two fragments struck each other too quickly, they could shatter into many smaller pieces. If their speed was more moderate, or if the material was still hot and soft, they were more likely to merge into a single mass. Larger bodies began developing gravity of their own, allowing them to attract nearby dust and rock. The more material they collected, the more massive they became, and the more effectively they could draw in additional fragments. The disk around Earth gradually changed as this process continued. The amount of loose material declined. A few larger bodies began to stand out among the countless smaller fragments. They continued colliding with one another, sometimes losing part of their material and sometimes merging into a still larger mass. After many encounters, more and more of the debris became concentrated into one dominant body. Accretion could not proceed equally well everywhere in the disk. Material too close to Earth experienced powerful and uneven gravitational forces. The side of a forming body nearest the planet was pulled more strongly than the side farther away, which could stretch the object apart or break it up. At a more favorable distance, fragments could remain held in orbit by Earth while still having enough freedom to combine into larger and more stable bodies. The young moon may have begun taking clearer shape within this favorable region. At first, it would not have been a smooth, evenly rounded world. Its surface changed continuously as new fragments struck it. Some areas gained additional material. Others were broken apart, and the ejected pieces either fell back or remained in orbit. As the growing body became more massive, its own gravity began pulling material toward the center, gradually making its shape more spherical. Temperatures remained extremely high throughout this process. Every time a large piece of rock struck the young moon, the energy of motion was converted into heat. Material compressed as the body grew also raised its internal temperature. So even while the ring around Earth was gradually cooling, the forming moon may still have maintained a molten outer layer or been repeatedly reheated by continuing impacts. Several large bodies may have existed within the debris disk at the same time. They orbited Earth together, collected smaller fragments, and altered one another's paths through gravity. Over time, some collided and merged. Others were shattered or fell back to Earth. Gradually, most of the available material became concentrated into one main body instead of remaining divided among many separate objects. As this body grew, it began influencing the disk that had created it. The gravity of the young moon pulled nearby fragments down onto its surface or changed their orbits. Some material was pushed back toward Earth, while other pieces were thrown farther away. The debris ring therefore became increasingly sparse, while the moon emerged more clearly as a separate celestial body. According to traditional models, the process of gathering most of the moon's mass may have taken anywhere from many months to several years, depending on the condition of the debris disk and the details of the impact. On a human scale, this is not an especially brief period. But within the billions of years of solar system history, it is almost an instant. A chaotic region of material could transform relatively quickly into a large body orbiting Earth. Even so, collecting most of its mass did not mean that the moon immediately became the world we see today. Its surface remained extremely hot. Its interior had not yet fully separated into distinct layers. Remaining debris continued to strike the surface and create new episodes of melting. The orbit of the young moon was also much closer to Earth and was still changing strongly under the gravitational interaction between the two bodies. There was no single clear moment when the moon did not exist, followed immediately by a fully completed moon. It grew little by little. A small body became a larger one, then continued gathering material until it was massive enough to maintain its shape and dominate the surrounding region of space. The moon gradually became itself through countless collisions rather than appearing as a finished sphere from the beginning. Seen from the present, it is difficult to imagine that a body as large as the moon could have begun as dust, molten rock, and scattered fragments. But that is the power of accretion. No individual fragment was the moon on its own. Only when they collided, merged, and were held together by gravity within a common body could a new world emerge. In the traditional explanation, this process may have lasted from many months to several years. More recent simulations, however, have raised a far more dramatic possibility. The moon may have been born much faster. In the traditional explanation, material thrown outward by the giant impact formed a hot disk of debris around Earth. The fragments continued colliding, merging, and growing through a process called accretion. Depending on the model, gathering most of that material into the moon may have taken anywhere from many months to several years. But some more recent studies have opened the door to another, more striking possibility. The earliest stage of formation may have happened extremely quickly, perhaps within only a few hours. This does not mean that the moon was certainly completed in a matter of hours. A more accurate understanding is that some newer simulations show how, immediately after the collision, material could have formed a large satellite directly and placed it into orbit around Earth. That mass would not yet have been the completed moon we know today, but it may already have contained a large portion of the moon's eventual mass. This possibility became clear only when scientists began using higher resolution simulations. A collision between two large celestial bodies cannot be recreated in a laboratory, so computers are used to reconstruct the event. In these simulations, the early Earth and the impacting body are divided into an enormous number of small elements. The computer then follows how each portion moves, becomes compressed, heats up, mixes with other material, and is thrown outward. The higher the resolution, the more finely the material is divided, allowing subtle motions to appear more clearly. In simpler models, the post-impact material often appears as a broad debris disk, but as the level of detail increases, scientists can see large streams of matter, temporary clumps, and the ways gravity pulls them together during the first few hours. Some simulations suggest that the material did not necessarily have to break completely into countless small fragments and then slowly accumulate. A large amount of hot rock may have been stretched into long streams around Earth. Under the right conditions, part of that flowing material could remain connected, rapidly gather into a large body, and enter orbit instead of falling back to the planet. If this process truly occurred, the moon's initial birth may have been far faster than traditional models suggest. Within only a few hours, a large satellite may already have appeared in the region around Earth. The remaining debris could then continue falling onto the new body, returning to Earth, or being thrown farther away. Direct formation and accretion would not necessarily exclude one another. A large body could have appeared early and then continued collecting additional material afterward. However, a satellite that formed within hours would not yet have been a cold, round, stable sphere. The newly formed mass would still have been extremely hot and may have been stretched or distorted by Earth's gravity. Its surface could have contained large amounts of molten rock, while other fragments continued falling onto it. Its initial shape, composition, and orbit would all still have been changing rapidly. Its distance from Earth would also have been critical. If the body formed too close to the planet, Earth's uneven gravitational pull could have torn it apart or caused it to fall back. If it was placed into a suitable orbit, most of the mass could survive and gradually become more stable. In some simulations, the newly formed body is stretched, loses part of its material on the side nearest Earth, yet the remainder continues moving in orbit. Rapid formation may also help explain why lunar material is so similar in many ways to the outer rocky layers of Earth. If a large satellite formed directly from streams of material pulled from both bodies, some models could produce a moon containing more Earth-derived matter than older simulations did. Even so, this is not a final answer, because the moon's composition also depends on the impact angle, velocity, the size of the impacting body, and the condition of Earth at the time. Even a small change in the initial conditions can produce a very different result. In some cases, the mass falls back to Earth. In others, it is thrown too far away. Different models may create a satellite with the wrong mass, composition, or orbit. So a simulation that produces a moon within a few hours shows only that such a process is physically possible. It does not prove that the real history unfolded in exactly that way. Every simulation is a simplified version of an extraordinarily complex event. Computers must estimate how rock melts, how matter vaporizes, how heat spreads, and how the internal layers of the two bodies mix. Although resolution continues to improve, no model can perfectly reproduce every detail of a collision that happened more than 4 billion years ago. The results must therefore be compared with lunar rocks, the moon's internal structure, its mass, and the present motion of the Earth-Moon system. The value of these newer simulations does not lie in completely replacing the traditional accretion model. Instead, they show that the moon may have had more possible paths to formation than scientists once imagined. A large body may have appeared very early and then continued growing from the surrounding debris disk, or the material may have passed through a longer period of accretion before the main body formed. The evidence currently available is still not sufficient to choose one scenario with complete certainty. Perhaps the most fascinating possibility is that the first moments after the impact were far more important than previously thought. Within only a few orbits around Earth, streams of hot material may have separated, encountered one another again, and formed a large mass. A body of significant size could have appeared before the debris disk had time to settle into a clearly defined structure. But forming within a few hours refers only to the appearance of a large satellite in orbit. The moon would still have needed more time to gather additional material, become more spherical, separate into internal layers, and stabilize its motion. Cooling would have taken far longer. The familiar craters, dark plains, and cold gray surface appeared only through later stages of its evolution. The possibility of rapid formation, therefore, does not make the story simpler. It gives the story a more powerful beginning. Only a few hours may have separated the giant impact from the appearance of a large satellite. Everything afterward was still a long journey of molten rock, collisions, cooling, and transformation. Whether it formed within a few hours or through a longer process, the young moon was certainly not yet the cold gray sphere we see today. Whether the moon's first large mass appeared within only a few hours or accumulated over a longer period, the young body could not yet have resembled the cold gray sphere we see today. It had just been born from rock heated, stretched, and driven into collisions by enormous energy. Fragments of material continued falling onto the surface while gravity compressed them into an ever-growing body. Much of that energy of motion was converted into heat, allowing the moon's outer layers to melt across an immense area. The early moon may therefore have been covered by a magma ocean. This was not an ocean of water, but a deep and widespread layer of molten rock across the surface. In place of the cold, dry, dust-covered terrain we see today was a red-hot world, where thick molten material moved slowly under the influence of heat and gravity. Regions that had only just begun to solidify could quickly be struck by another fragment, shattered, and melted again. Magma is simply rock heated until it enters a liquid state. On Earth today, magma is usually found deep beneath the crust and reaches the surface only during volcanic eruptions. On the young moon, melting may not have been limited to a few small regions. Heat left from the impact, energy released during formation, and continuing collisions may have created a layer of liquid rock covering most of the surface. That magma ocean did not remain still. Hotter material rose from below, while cooler material sank. These continuous currents carried heat from deep inside toward the surface, slowing the process of solidification. Even so, the moon continued radiating heat into space. As temperatures gradually fell, the first minerals began crystallizing out of the molten rock. The minerals did not all appear at the same time, and they did not all have the same density. Some types that formed early tended to sink deeper into the magma ocean. Lighter crystals, however, could gradually float upward, This process began reorganizing the moon's interior instead of allowing it to remain a nearly uniform mixture of molten material. One especially important light mineral was plagioclase, a mineral rich in calcium and aluminum. As plagioclase crystals formed, they were less dense than the surrounding magma and tended to rise toward the surface. Over time, more and more crystals accumulated and joined together, creating the moon's first crust. That early crust may have resembled bright rafts of rock floating on a sea of hot material, gradually connecting as the moon continued to cool. But the process was not smooth or uniform. Beneath the newly forming crust, magma was still moving. Above it, remaining fragments continued falling onto the surface. A region that had just solidified could be shattered, reheated, or mixed with deeper material. The moon, therefore, did not change from molten to solid in a single moment. The crust formed in separate regions was altered and then continued thickening. The surface cooled first because it was directly exposed to space, while deeper regions retained heat for much longer. As the solid crust grew thicker, it also made it more difficult for heat beneath it to escape, allowing some pockets of magma to survive for extended periods. Some light-colored lunar rocks are thought to preserve traces of this ancient crust. They are often rich in plagioclase and belong to a type of rock known as a northocite. The name matters less than the story the rocks carry. These bright fragments may once have been light crystals that floated upward from the magma ocean and then joined together to form some of the moon's earliest solid surface. Today, the moon's bright highlands still contain abundant material connected to this ancient crust, but the surface has endured more than 4 billion years of impacts. Meteorites repeatedly created craters, ground rock into dust, and mixed material from different depths. The original crust is no longer preserved as one untouched layer, yet the surviving fragments still contain enough information for scientists to trace the moon's earliest history. Age measurements suggest that some parts of this ancient crust may have formed more than 4.4 billion years ago. That takes us back to a time not long after the moon's birth. Determining an exact age, however, is not simple. A crystal may have formed very early and then later been reheated by an impact, altering part of the chemical record preserved within it. For this reason, many questions remain about how the magma ocean cooled. Scientists do not fully agree on how deep the molten layer was, how long it survived, or how strongly later impacts remelted the crust. A thin crust may have appeared fairly early, while deeper regions remained molten for much longer. At that time, the moon may already have had a solid surface while still remaining hot and dynamic inside. As the magma continued cooling, the moon also began separating into internal layers. Denser material sank, while lighter material became concentrated nearer the surface. This process is often called differentiation. Put simply, the moon began arranging its internal structure. Heavier material moved deeper, while lighter material formed the outer crust. That separation did not happen in complete calm. Sinking minerals could destabilize the interior and keep different layers in motion. The remaining magma also changed in composition as minerals crystallized and left it. Some molten regions enriched in particular elements may have remained just beneath the crust, later influencing volcanic activity. Long after the ancient crust began forming, magma from the interior could still rise through fractured regions. Lava filled large basins created by impacts and then cooled into the dark plains visible on the surface today. The modern moon therefore preserves many different layers of history. The very old bright crust formed from the magma ocean and darker regions created later by volcanic activity. The greatest importance of the magma ocean lies not only in the image of a world covered by molten rock. As the magma began crystallizing, minerals also began preserving chemical traces of time. Within the structure of a tiny crystal, certain elements can be trapped and then change at measurable rates. In this way, rock becomes a natural clock. These mineral grains may be no larger than grains of sand, yet they can still preserve evidence of when the lunar crust first began to appear. They help scientists estimate the ages of rocks, identify later episodes of reheating, and reconstruct parts of the moon's cooling history. A world that had once been an ocean of molten stone began recording its own past as soon as its first crystals formed. The magma ocean, therefore, connects the moon's violent birth with the rock samples studied today. The impact produced heat. That heat melted rock. Cooling then caused minerals to separate and the first crust to appear. The moon did not immediately become a quiet world, but it developed a surface durable enough to begin preserving traces of time. As the molten rock cooled, the moon began storing its memories within tiny mineral grains. As the molten rock cooled, the moon began preserving its memories within tiny mineral grains. Some were so small that they could be hidden inside a pinch of dust and remain almost invisible to the naked eye. Yet within those crystals, time left a measurable trace. Because of that, a small piece of material brought back from the moon can allow humanity to look more than 4 billion years into the past, to a time when the moon was only beginning to develop a solid crust. The mineral that plays this special role is called zircon. Zircon can form as magma cools and crystallizes. It is not the most abundant mineral in lunar rock, but it is extremely valuable for determining age. Its crystal structure is highly durable, capable of surviving across immense spans of time while preserving certain elements from the moment it formed. Each zircon grain is therefore like a tiny sealed archive locked inside the rock. The crystals examined in this case were found in material returned to Earth by Apollo 17. In 1972, astronauts from the final mission of the Apollo program collected rocks and soil from the lunar surface. At the time, no one could fully know how many stories those samples would still be able to tell. More than half a century later, increasingly precise instruments allow scientists to study them at nearly the scale of individual atoms. Zircon is especially useful because, when it forms, it can incorporate uranium into its crystal structure, while usually containing very little lead at the beginning. Uranium is not completely stable. Over time, some uranium atoms gradually transform into lead at a well-known rate. By measuring how much uranium remains and how much lead has been produced, scientists can estimate how much time has passed since the zircon crystal first formed. This method is called radiometric dating. The name may sound complicated, but the principle can be imagined as a natural hourglass. At the beginning, most of the sand is in the upper chamber. Over time, it falls into the lower chamber at a predictable rate. If we know that rate and measure how much sand remains in each chamber, we can calculate how long the hourglass has been running. In zircon, uranium is like the original material, while lead is the product that gradually appears over time. Of course, the clock inside a mineral is not as simple as a real hourglass. A zircon grain may have endured impacts, high temperatures, and other changes throughout the moon's history. If lead shifts within the crystal or escapes from it, the calculated age can be affected. For this reason, scientists do more than count uranium and lead. They also examine how those atoms are distributed and whether they have gathered into small clusters because of a later heating event. In a study published in 2023, the research team used a technique capable of examining material at an extremely small scale. The zircon sample was prepared into a very fine, needle-shaped tip, and atoms near its surface were then removed and identified one by one. This method allowed the researchers to examine the distribution of lead within the crystal in great detail and determine whether the radiometric clock still preserved its original ancient signal or had been disturbed. The results supported an age of about 4.46 billion years for the zircon in the Apollo 17 sample. This date reaches back very close to the beginning of the solar system. However, the crystal does not prove that the impact that created the moon occurred at exactly that time. Zircon could form and survive only after the magma in which it developed had cooled sufficiently. If the moon's outer layers were still violently molten, such a small crystal would have had difficulty forming and remaining preserved. The age of the zircon therefore establishes an important limit. The moon had to exist before the crystal appeared. The collision, The gathering of material into a satellite, and the cooling of at least part of the magma ocean all had to occur earlier, or not much later than the date recorded in the crystal. In other words, the 4.46 billion year old zircon shows that the moon is at least that ancient, even though its true formation may have occurred earlier. The significance of this finding lies in more than simply changing a number. If the moon already contained zircon crystals this old, then the earliest stages of its history may have unfolded very soon after the solar system formed. Following the giant impact, material had to be placed into orbit, gather into the young moon, melt across a large scale, and then begin cooling enough for minerals to crystallize. All of those steps would have taken place within a relatively short interval after the birth of the solar system. A single zircon grain does not tell the entire story. It records conditions at one place and one particular moment. Other regions of the moon may have cooled faster or more slowly. Some ancient crystals may have been destroyed by impacts. The grains that survived until today represent only a very small fraction of the material that once existed. Scientists must therefore compare many samples, many measurements, and different minerals before reconstructing the broader history. The reheating of lunar rocks also makes the story more complicated. Over billions of years, the moon endured countless impacts of different sizes. A powerful collision could melt rock locally, create new minerals, or alter older crystals. If researchers looked only at one age measurement without considering its geological setting, they might mistake the age of a later impact for the age of the first crust. Zircon has an advantage because it is highly resistant. A crystal can survive events that destroy or completely alter many other minerals. Even so, it is not invulnerable. Heat and pressure can still leave traces inside it. Those traces can sometimes help scientists recognize that the grain passed through several stages. It formed extremely early, was later affected by an impact, and then continued surviving within the rock until it was brought back to Earth. We can imagine that history as being written in many extremely thin layers. The center of the crystal may preserve the age of its original formation. Regions nearer the surface may reflect a later episode of heating. Uranium and lead atoms within it continue changing in silence, requiring no light and no visible motion. Across billions of years, this tiny clock continues running. When the Apollo 17 sample was placed inside a laboratory, the distance between the ancient past and the present was compressed into a single mineral grain. The astronauts needed only a few days to bring the sample back to Earth, but the material within it had lived through nearly the entire history of the moon. It existed when the moon was still hot, endured later impacts, and rested beneath the surface until it was collected. This is also why old samples continue producing new discoveries. The technology used to examine them today did not exist when Apollo 17 left the moon. Preserving the rocks for decades allows later generations to return to the same material with new questions, measure it at far greater detail, and uncover signals that were once beyond our ability to observe. An age of about 4.46 billion years provides an early marker in the moon's history, but it does not end the debate. Researchers must still determine how quickly the magma ocean cooled, how the first crust formed, and how many ancient signals were altered by later events. One crystal can provide an anchor for the timeline, but the spaces around that anchor must still be filled by other samples. What matters most is that, from something nearly invisible to the naked eye, humanity can place a limit on the age of an entire celestial body. No clock needed to survive from the beginning of the solar system. Matter itself became the clock. Atoms changed slowly, while the crystal preserved the results of that change across a span of time far longer than the whole history of humanity. The tiny zircon grain therefore connects many stages that may seem separate. The giant impact, the molten moon, the first solid crust, later collisions, and the Apollo 17 mission. All of them meet in a measurement performed on Earth. From that point, part of the moon's timeline begins to come into clearer focus. But the moon's age is not the only clue. its composition raises an even more difficult question. The tiny zircon grains allow scientists to place a very early marker on the Moon's timeline. But age answers only one part of the story. When the samples returned by the Apollo program were examined more closely, they revealed something far more puzzling. In appearance, environment, and surface history, the Moon is very different from Earth. Yet at a deep chemical level, the two bodies are astonishingly similar. According to the giant impact hypothesis, the Moon formed from material thrown outward when the young Earth collided with another planetary embryo. If most of the Moon's raw material came from the impactor, we might expect lunar rocks to carry a clearly different chemical signature. That body may have formed in another region of the solar system from material with a composition slightly different from Earth's. But when scientists compared the samples, many results showed that the Moon and Earth carry unusually similar traces. One of the most important tools for identifying this similarity is the study of isotopes. Isotopes can be understood as slightly different versions of the same element. They contain the same number of protons, so they remain the same element, but they have different numbers of neutrons in their nuclei, and therefore slightly different masses. Oxygen in rock, for example, can exist in several isotopic forms. All of them are still oxygen, but the proportions of those different versions can vary very slightly from one celestial body to another. These differences are usually far too small to be seen or detected through ordinary analysis. With highly precise instruments, however, isotope ratios can be measured with great care. By comparing those ratios, scientists are essentially matching the chemical fingerprints of different worlds. Two rock samples may contain the same elements, but if their isotope ratios differ, they may have formed from different sources of material or passed through different histories. Many bodies in the solar system have their own isotopic fingerprints. Meteorites belonging to different groups of material do not match Earth perfectly. Mars also leaves a distinctive signature in meteorites known to have come from that planet. This shows that material in the early solar system was not mixed with perfect uniformity. Different regions around the Sun may have preserved slightly different isotope ratios and passed those characteristics onto the planets that formed there. Lunar samples therefore produced a major surprise. Oxygen isotope ratios in many moon rocks are extremely close to those found in rocks from Earth's outer layers. Oxygen is not the only example. Other isotope systems, including titanium and tungsten, also reveal a very close relationship between the two bodies. This does not mean that every component of lunar rock is completely identical to rock from Earth. The Moon is poorer in certain volatile substances, has a different internal structure, and experienced its own geological history. Yet in several important isotopic fingerprints, the degree of similarity is still greater than early impact models could easily explain. This is exactly what makes the giant impact hypothesis both stronger and more complicated. The similarity shows that the Moon is deeply connected to Earth. It supports the idea that material from Earth's outer layers made a significant contribution to the satellite's formation. The Moon does not appear to be a completely foreign body that was simply captured by Earth. It seems to have emerged from the same material story as our planet. But in many traditional impact models, most of the debris disk that formed the Moon was predicted to come from the impacting body. If that object had a chemical fingerprint different from Earth's, the Moon should have preserved some of that difference. The fact that lunar rocks resemble Earth so closely forced scientists to question the proportion of material contributed by each body, the degree of mixing that followed, and even the origin of the vanished planetary embryo. One possibility is that the impact mixed the material far more thoroughly than simpler models once suggested. After the two bodies collided, molten rock and rock vapor may have created an intensely hot environment around Earth. Material from Earth, the impactor, and the debris disk could have exchanged with one another before the Moon solidified. If the mixing was strong enough, the original isotopic differences may have been blurred, leaving the Moon with a signature much closer to Earth's. Completely mixing such a vast amount of material within a short period, however, is not easy to demonstrate. The debris disk was constantly moving, cooling, and accumulating. Different regions may not have exchanged material evenly. Different elements also respond differently to high temperatures. A model that explains the similarity must therefore describe several processes at once: the collision, the distribution of heat, the motion of rock vapor, accretion, and the moon's final composition. Another possibility is that the impactor formed close to Earth. If the two bodies grew within the same region of the early solar system, they may have gathered material from nearly identical sources. Their isotopic fingerprints may therefore have been fairly similar even before the collision. The impact could still have created the moon, while the chemical resemblance would not need to come entirely from mixing afterward. This idea sounds reasonable, but it also raises a question of probability. Two separate celestial bodies are not usually expected to have perfectly matching compositions, even if they formed relatively close together. Meteorite samples show that the young solar system contained many distinct groups of material. So if the planetary embryo and Earth truly had nearly identical fingerprints, scientists still need to explain why those two worlds were so alike from the beginning. Some models change the nature of the collision itself. Instead of a smaller planetary embryo striking Earth in a relatively simple scenario, perhaps the two bodies were closer in mass, or perhaps Earth was rotating extremely rapidly before the impact. Conditions like these could place more Earth material into orbit, allowing the moon to form mainly from the outer layers of Earth itself. If so, the isotopic similarity would become easier to understand. But every change introduces new questions. The model must produce a moon with the correct mass, place it in an orbit capable of evolving into the present system, and preserve the proper total rotational motion of Earth and the moon. It must also explain the moon's small iron core, its depletion in certain volatile substances, and the evidence in its rocks of extremely high temperatures. A successful answer cannot match the isotopes while ignoring the other features. High-resolution simulations offer another possibility. If a large satellite formed directly within the first hours after the impact, streams of material from Earth may have contributed more strongly to the moon's outer layers. This could help produce a chemical fingerprint close to Earth's without requiring the entire debris disk to mix with perfect uniformity. Even so, this remains an active line of investigation, not a final conclusion. The similarity between rocks from Earth and the moon is not absolute. As measurements have become more precise, scientists have identified extremely small differences in certain isotope systems and in chemical composition. Those subtle differences may preserve information about the proportion of material contributed by each body, the temperature of the impact, or the substances lost during formation. The remarkable point is therefore not that the two worlds are identical, but that they are so similar while still preserving delicate differences. Those small deviations may be just as important as the similarities. If the moon were completely identical to Earth, one might conclude that it formed only from Earth material. If it were too different, the idea of a deep relationship between the two bodies would become weaker. Reality lies between those extremes. The moon resembles Earth closely enough to reveal a strong shared origin, yet differs enough to remind us that its formation included another component and a history of its own. The Apollo samples therefore do more than help measure the moon's age. They serve as a test for every model of the giant impact. A simulation may produce a satellite of the correct size, but if its isotopic composition differs too greatly from Earth's, it still has not explained the real moon. Conversely, a model may create the correct chemical similarity, but if it cannot keep the satellite in a stable orbit, it is not convincing enough. This is why the story of the moon's origin remains unfinished. The giant impact hypothesis explains many important features: the angular momentum of the system, the moon's small core, evidence of melting, and the existence of a debris disk around Earth. But the isotopic fingerprints require the model to become more refined. The collision must not only create a moon, it must create a moon so similar to Earth that tiny pieces of rock carry a signature, suggesting they belong to almost the same family of material. Within every lunar sample, the elements quietly preserve their origins. The ratios between tiny isotopes become evidence of a relationship deeper than any resemblance visible from a distance. The moon may have been born from an event that shattered two celestial bodies, but its composition shows that what remained after that event was not entirely foreign to Earth. If the impactor came from somewhere else, why does the moon resemble Earth so closely? If Theia came from somewhere else, why does the moon resemble Earth so closely? That question lies at the center of one of the most difficult problems in the giant impact hypothesis. The collision remains convincing because it explains many important features of the Earth-Moon system. Yet as lunar samples are measured with greater and greater precision, their isotopic fingerprints reveal an unexpectedly close relationship with Earth. If the moon contains a large amount of material from Theia, we might expect its rocks to preserve a distinct chemical signature from that body. Planets and meteorites that formed in different regions of the solar system often have slightly different isotope ratios. The differences are extremely small, but still large enough to reveal where the material came from. A separate world like Theia should therefore have possessed a fingerprint of its own, even if it differed from Earth's by only a tiny amount. And yet many lunar samples are so close to rocks from Earth that the differences are difficult to detect. This is often called the isotopic problem of the giant impact hypothesis. It does not mean that the hypothesis is entirely wrong. Instead, it forces scientists to look more carefully at what actually happened during the collision, where Theia came from, and how the material of the two bodies mixed before the moon was born. One possibility is that Theia did not form very far from Earth. In the young solar system, many planetary embryos grew together from the disk of gas and dust orbiting the Sunday. If Earth and Theia formed in nearby regions, they may have gathered material from almost the same source. Their isotopic fingerprints could therefore have been fairly similar from the beginning. Under this explanation, the moon would not have needed to erase Theia's signature after the impact, because that signature may never have been very different from Earth's. The two worlds grew like neighbors within the same region of material and eventually collided. The rocks that formed the moon could therefore have had a composition close to Earth's, even if a substantial amount came from Theia. However, forming nearby does not guarantee that two celestial bodies will be completely alike. Even within a relatively small region of the early solar system, material may not have been mixed evenly. Large bodies grew through many random collisions and collected different groups of material. The idea that Theia had a fingerprint similar to Earth's is therefore plausible, but it still leaves the question of why the resemblance was so strong. A second possibility lies in the power of the collision itself. Perhaps the event did more than melt rock and throw material into orbit. It may also have mixed Earth and Theia on an enormous scale. After the impact, an extremely hot region of rock, vapor, and magma may have surrounded the planet. Within that environment, material from the two worlds could have exchanged, circulated, and gradually become more uniform before the moon accumulated. If the mixing was strong enough, Theia's original fingerprint may have been blurred. The material that formed the moon would no longer represent either body alone, but a mixture of both. As that mixture cooled and gathered together, the moon could have developed a composition much closer to Earth's outer layers than simple impact models originally predicted. But mixing such an immense amount of material evenly would not have been easy. The debris disk was constantly orbiting Earth, with different regions at different temperatures and densities, while cooling and accretion may have begun quite early. The material needed enough time to exchange before becoming locked inside new masses of rock. If the moon formed very rapidly, the time available for mixing may have been even shorter. Scientists must therefore consider not only how powerful the collision was, but also the physical condition of the material afterward. Did the rock melt completely? How much of it became vapor? Did material from Earth and Theia enter the same region, or was it separated into different orbits? How long did the debris disk survive before the moon began to form? Every one of these factors could influence the final degree of similarity between the two bodies. A third possibility is that the original impact model needs to be revised. In the traditional picture, a body roughly the size of Mars struck the young Earth at an angle. The collision placed mostly Theia's material into orbit, while most of Earth remained within the planet. That model successfully produced a debris disk and a moon with many appropriate features, but it also made the moon too likely to preserve a strong Theian signature. Some newer scenarios change the angle of impact, the speed of the collision, or the sizes of the two bodies. Certain models suggest that Earth was already rotating very rapidly before the impact, allowing more material from Earth's own outer layers to be placed into orbit. Other models imagine two bodies closer to one another in mass, causing their material to mix more strongly and be redistributed in a different way. If the moon formed from a greater proportion of Earth material, its isotopic similarity becomes easier to explain. Every change, however, must satisfy many conditions at the same time. The model must create a moon with the correct mass and a relatively small iron core, place it into an orbit capable of evolving into the system we see today, and avoid producing a total rotational state for Earth and the moon that differs too greatly from observations. One model may explain the isotopes well, but create a moon that is too large. Another may produce the correct size, but cause the satellite to fall back to Earth. In some cases, the chemical composition may fit while the rotational motion of the system does not. One part of the story cannot be repaired, while all the others are ignored. High-resolution simulations have opened another possible path. They show that a large satellite may have formed directly during the first few hours after the collision, instead of being built entirely from a long-lived debris disk. In some cases, the outer layers of the newly formed satellite receive a substantial amount of material from Earth. This could help explain why lunar rocks carry a fingerprint so close to that of our planet. Even so, a simulation result only shows that a process is possible under a particular set of conditions. It does not prove that the real history unfolded in exactly that way. Scientists must still compare the results with lunar rocks, mineral ages, the abundance of volatile substances, the size of the moon's core, and its present orbit. Each piece of evidence is like one part of a case file, and no single piece can decide the entire story. It is also possible that the truth lies somewhere between several explanations. Theia may have formed relatively close to Earth, making its original composition not too different. The collision may then have mixed material from both bodies even more thoroughly. At the same time, the moon may have received more material from Earth's outer layers than the earliest models predicted. The present similarity does not necessarily need to have been produced by only one mechanism. The extremely small differences between rocks from Earth and the moon are also important for distinguishing among these possibilities. If the two bodies were completely identical across every isotope system, either their common origin or the degree of mixing would have needed to be extraordinarily strong. If small deviations remain, they may represent surviving traces of Theia. Measuring those deviations requires highly precise instruments and carefully preserved samples. The problem becomes even more difficult because Earth has not preserved the same surface composition it had at the time of the impact. More than 4 billion years of geological activity have continuously recycled the crust, carried material deep into the planet, and brought it back again. The moon has also been struck and melted repeatedly. The rocks available today are survivors of a long history, not untouched fragments freshly separated during the collision. Theia no longer exists as a separate celestial body from which samples can be collected and compared. If most of it merged into Earth and the moon, its traces must be found indirectly within internal structures, isotope ratios, and simulation results. This is why the search for Theia resembles an investigation in which the main witness has disappeared and the scene has been altered over billions of years. The uncertainty, however, does not make the giant impact hypothesis meaningless. A scientific hypothesis is not strong because it avoids every question, but because it can be tested, adjusted, and compared with new evidence. The isotopic problem showed that the earliest models were too simple, but it also encouraged more detailed research into the impact, the mixing of material, and the moon's earliest formation. Every new result narrows the range of what may have happened. A model that fails to match the isotopes becomes less likely. A model that cannot produce the correct orbit is also difficult to accept. New samples, more precise measurements, and more powerful simulations continue filtering the possibilities. The story becomes clearer not because every mystery disappears, but because explanations that do not fit are gradually recognized and set aside. The case of Theia, therefore, remains open. Perhaps it resembled Earth from the moment it formed. Perhaps the collision mixed the two worlds more deeply than we once imagined. Or perhaps the real impact scenario differed significantly from the traditional picture. Each possibility explains part of the evidence, but none of them alone has yet answered every question. What remains is not a weaker story, but a deeper one. Lunar rocks do not simply confirm or reject the collision. They force us to ask how the impact unfolded, where the material came from, and how completely the two bodies blended together. Within the smallest differences between atoms, the history of a vanished world may still be preserved. To test those possibilities, scientists must reconstruct a collision that no one ever witnessed. To test the possibilities that remain open, scientists must reconstruct an event that left no witnesses behind. The collision occurred about 4.5 billion years ago, when Earth was still very young and the moon had not yet appeared. The body that once struck our planet no longer exists intact. Its remains may have merged into Earth, become part of the moon, or been scattered into space. The original scene has vanished, but the consequences of the event are still here. Earth has a particular rotation rate. The moon has a specific mass, structure, and orbit. Rocks from both bodies preserve closely related chemical signatures. All of these become constraints that any explanation must satisfy. A planetary collision cannot be created in a laboratory, nor can humanity travel backward in time to observe it. Instead, supercomputers are used as digital laboratories, where different scenarios can be tested again and again without destroying a real world. Within this digital space, the early Earth is placed in the path of an approaching body. Researchers choose its size, speed, and angle of approach, then allow the laws of physics to determine what happens next. Sometimes the two bodies merge almost completely. In other cases, much of their outer rock is stretched into long streams of hot material. In still other simulations, a large amount of debris escapes too far away to form a satellite. Even a small change can produce a completely different result. A nearly head-on collision transfers energy differently from an angled, glancing impact. A higher speed heats the rock more intensely and throws more debris farther away. Earth's rotation before the event also affects the direction in which its outer layers are pulled. The past is therefore not reconstructed through a single calculation, but through many competing versions. To allow the computer to follow the event, the two bodies are divided into enormous numbers of small elements. Each one represents a quantity of rock or metal and carries information about its position, temperature, mass, and velocity. When the collision begins, these elements are compressed, heated, stretched, mixed, or launched into orbit. The greater the level of detail, the more clearly motions that were previously hidden begin to appear. Streams of rock no longer look like a single blurred cloud. The computer can track where Earth's outer layers go, which parts of the impactor merge into the planet, which parts form a debris field, and whether a large body can appear during the first few hours. The resulting images may resemble a film of the ancient past, but they are not photographs of history. They show only what could happen when a particular set of starting conditions is entered into the calculation. Even a visually impressive result may be wrong if the final body does not resemble the real moon. This is the most difficult part of the reconstruction. Producing a mass that orbits Earth is not enough. That body must have approximately the correct size, contain no excessive amount of metal, and occupy an orbit capable of evolving into the one we observe today. Earth must also emerge from the event without rotating at an unreasonable speed. The entire system must preserve the proper amount of angular momentum. The moon has a relatively small metallic core. This suggests that most of the material that formed it came from the outer rocky layers rather than the iron-rich cores of the two bodies. In every reconstruction, the path taken by the metal is therefore extremely important. If too much iron is placed into orbit, the resulting satellite will differ from the moon we know. Chemical composition creates an even more difficult challenge. Lunar rocks carry many isotopic signatures that are close to those of Earth rocks. The material thrown outward, therefore, cannot have come only from a world with a completely different composition. The impact must either place enough Earth rock into orbit or produce mixing strong enough to reduce the original differences to very small levels. But a scenario that solves the chemical problem may create difficulties with motion. For example, allowing Earth to rotate extremely rapidly before the impact can help place more of the planet's own rocky outer layers into orbit. This makes the similarity between Earth and the Moon easier to explain, but in some cases it leaves too much angular momentum in the entire system. By contrast, a gentler collision may create a more suitable orbit, but the resulting satellite may contain too much material from the vanished impactor. Its chemical fingerprint would then be difficult to reconcile with the Apollo samples. Every time one detail is adjusted, the rest of the story changes with it. Temperature is another important constraint. The event must have been powerful enough to melt an enormous amount of rock, create a debris disk, and produce a magma ocean on the young moon. Yet the temperature cannot be chosen arbitrarily. If too much rock becomes vapor, and nearly all volatile substances are lost, the final composition will no longer resemble what is measured in real samples. A supercomputer is therefore not searching for the most violent possible collision. It is searching for an event precise enough to satisfy many conditions at once, powerful enough to create a satellite without destroying the entire system, hot enough to explain the history of melting while still preserving the correct composition, and chaotic enough to mix material from two worlds while still leaving behind a stable Earth and Moon. Many reconstructions end in failure. A satellite appears and then immediately falls back. The debris disk contains too little mass. The newly formed body is thrown too far away. Its core contains too much iron. Its composition does not resemble Earth. Its orbit cannot evolve into the present state. These failed results are not useless. They eliminate paths that were unlikely to have occurred and gradually narrow the range of possible histories. Science does not always advance by finding the correct answer immediately. Sometimes it moves forward by identifying with increasing clarity what history could not have done. Across generations of calculations, several notable possibilities have begun to emerge. Some scenarios use a smaller body striking Earth at an angle. Others involve two bodies closer to one another in mass. Certain models assume that Earth was rotating very rapidly before the impact. More recent studies also suggest that a large moon-like body could have appeared directly during the first few hours rather than waiting for the entire debris disk to accumulate slowly. These possibilities do not simply replace one another. They represent different attempts to explain the same collection of evidence. The real history may have resembled one of them, or it may lie somewhere between several possibilities, with a large body forming early and then continuing to gather material from the surrounding debris. The strength of a supercomputer lies in its ability to test events that humanity could never create. Within a few simulated hours, a planet can be distorted, its rocky outer layers stretched into long ribbons, its metallic cores merged, and a new satellite brought into existence. Every simulation is a hypothetical past placed under examination. But a computer can work only with the laws and conditions supplied by humans. The behavior of molten rock, under extreme pressure, remains very difficult to describe perfectly. The transition between liquid rock and vapor, the degree of mixing, and the rate at which heat escapes all require approximations. Higher resolution reveals more detail, but it does not turn a simulation into a camera capable of filming the past. The results must therefore always return to the real moon. Rock samples reveal ages and composition. Gravitational data reveal the interior structure. The present orbit preserves the consequences of billions of years of energy exchange with Earth. The rate at which the moon is moving away also helps scientists work backward toward its original distance. Each source of evidence tests a different part of the story. Rock samples can reject a scenario that produces the wrong composition. The structure of the core can eliminate impacts that send too much metal into orbit. The motion of the system limits the possible speed and angle of approach. Only when many traces agree does a scenario become more credible. The reconstruction is therefore like assembling a case file from which most of the documents have been lost. The supercomputer attempts to fill the empty spaces. The moon tests whether those additions are reasonable. When new data appear, the entire picture may need to be revised. This does not make the research unreliable. On the contrary, it shows that the past is being tested with increasing rigor. An explanation is not preserved merely because it sounds compelling. It must pass multiple tests of physics, chemistry, and motion at the same time. Perhaps one day, more advanced simulations will narrow the history to a very small group of possibilities. Even then, the results will still need to be compared with rocks, minerals, and real traces preserved on the moon. A computer can show how a lost world might have struck Earth. It cannot create evidence that one particular scenario truly occurred. After billions of calculations, the past appears more clearly, but the case is not fully closed. Some paths have been eliminated. The remaining possibilities have become more detailed, more tightly constrained, and more consistent with the Earth-Moon system we see today. The collision is no longer only a general idea, but an event tested one element at a time: size, angle of approach, temperature, motion, and composition. Yet no matter how sophisticated the simulations become, the real moon still holds evidence that a computer cannot create on its own. The moon's birth did not end when a new satellite appeared around Earth. At that time, the two bodies were much closer together, far hotter, and more strongly affected by each other's gravity than they are today. From there began a process lasting billions of years, during which the moon's orbit gradually expanded while Earth's rotation slowed. Today, the average distance between Earth and the moon is about 384,400 kilometers. But the young moon did not form at its present location. Models suggest that it was once significantly closer to Earth, although its exact original distance depends on how the impact and the formation process unfolded. The moon is not moving away because Earth's gravity is disappearing. The reason lies in the exchange of energy between Earth's rotation and the moon's orbit. The moon's gravitational pull slightly distorts Earth, creating tides in the oceans and even within the planet's rocky body. Earth rotates on its axis faster than the moon travels around it. Because of this, the tidal bulges do not remain perfectly aligned with the line connecting the two bodies. Instead, Earth's rotation carries them slightly ahead. Those bulges exert a small gravitational pull on the moon, drawing it forward in the direction of its motion and transferring additional energy into its orbit. As the moon gains energy, it moves into a wider orbit. At the same time, Earth loses a small amount of rotational energy and slows down very slightly. This is a continuous exchange. The moon gradually moves farther away, while the length of a day on Earth increases little by little. Today, the moon is receding from Earth by about 3.8 centimeters each year. That distance is almost insignificant within a human lifetime. But when the same process continues over millions and billions of years, very small changes can alter an orbit substantially. This rate is measured using reflector panels placed on the lunar surface. Observatories on Earth send laser pulses toward them and measure how long the light takes to return. These highly precise measurements allow the distance between the two bodies to be tracked across many years. However, the rate of 3.8 centimeters per year was not necessarily constant throughout the Moon's history. When the Moon was closer, tidal forces were stronger. The shapes of the oceans, the positions of the continents, and Earth's rotation rate were also different from what they are today. There may therefore have been periods when the Moon moved away more quickly, as well as times when the process slowed. When the Moon was close to Earth, it would have produced much stronger tides. It would also have appeared larger in the sky, although no humans existed to see it. Earth was still young, rotating rapidly, and changing continuously, while the Moon was gradually cooling and settling into a more stable orbit. Tidal forces also slowed the Moon's own rotation. Eventually, the time required for the Moon to rotate once on its axis became equal to the time it took to complete one orbit around Earth. This is why we now see nearly the same side of the Moon at all times. The Moon still rotates, but its rotation has become synchronized with its orbit. The present distance is therefore not a fixed condition that has existed since the Moon was born. It is the result of a relationship that has changed continuously over billions of years. Every small distance the Moon has gained has been accompanied by a small amount of rotational motion, lost by Earth. The process is still continuing. The Moon is slowly widening its orbit, while Earth's rotation is not perfectly unchanging. The difference is far too small to notice within a single day or even a human lifetime, but it is large enough to rewrite the history of both bodies across geological time. As the Moon gradually moved farther away, Earth changed as well. Even the length of a day was once very different. As the Moon gradually moved farther away, Earth also began rotating more slowly. These two changes happened together and were directly connected. The energy that allowed the Moon to move into a wider orbit came from part of Earth's rotational motion. Over billions of years, the length of a day on our planet slowly increased. Today, Earth takes about 24 hours to complete one rotation on its axis. That rhythm is so familiar that it is easy to assume a day has always been this long. But 24 hours was not fixed from the moment Earth formed. In the distant past, the planet rotated faster, so each day was shorter than it is now. Soon after the Moon formed, the young Earth may have been spinning at a very high rate. Different models do not produce exactly the same numbers, but they all suggest that days were significantly shorter. The sun would have risen, crossed the sky, and set more quickly. A year would still have been close to the time Earth needed to orbit the sun, but because each day was shorter, there would have been more days in a year. The reason Earth gradually slowed lies in the Moon's gravity. That pull does not act equally everywhere. The side of Earth closer to the Moon is pulled slightly more strongly than the far side. This difference causes ocean water to rise into gentle bulges. Even Earth's rocky body is stretched and deformed by a very small amount. Earth rotates faster than the Moon travels around it, so those tidal bulges do not remain directly beneath the Moon. The planet's rotation carries them slightly ahead. The Moon continues pulling on those displaced bulges, creating a very small drag on Earth's rotation. Earth can be imagined as a large spinning wheel. The Moon does not stop the wheel, but every day it applies an extremely gentle braking force. Over a short period, the change is almost impossible to detect. But when that braking continues for millions and billions of years, the planet's rotation slows by a significant amount. Ocean water also creates friction as it moves across the seafloor, enters shallow seas, and reaches coastlines. Part of the energy of Earth's rotation is converted into heat and then dispersed. This process is called tidal friction. Put simply, the motion of the oceans removes a tiny amount of Earth's rotational energy over time. That energy does not disappear completely. Part of it is transferred to the Moon, allowing its orbit to expand. So as Earth rotates more slowly, the Moon moves farther away. These are two results of the same process. The day becomes longer, while the distance between the two bodies gradually increases. The change during a single year is extremely small. No one can feel the length of the day increasing simply by looking at a clock. But modern instruments can measure very subtle changes in Earth's rotation. Over geological time, those tiny differences accumulate into major changes. Evidence of shorter days is also preserved in rocks and fossils. Some ancient organisms formed regular growth layers, almost like tiny rings, recording the rhythms of days and years. By studying them, scientists have found that a year once contained more days than it does now. This means that each day must have been shorter than 24 hours. Earth, however, did not slow at the same rate during every period. The shapes of the oceans and the positions of the continents have changed continuously. At some times, ocean water moved in ways that created more friction. At others, the geometry of ocean basins allowed tides to dissipate less energy. The lengthening of the day therefore followed a complex rhythm rather than increasing as evenly as the hands of a clock. The moon was also once closer, which produced much stronger tides. During the early stages, it may have slowed Earth more rapidly than it does today. As the orbit expanded, that influence gradually weakened. The relationship between the two bodies has therefore always been changing. Greater distance reduces the strength of the pull, but the exchange of energy continues. A 24-hour day is only the present result of that long history. It is not an unchanging number built into Earth. In the past, days were shorter. In the distant future, if the exchange with the moon continues, they will become longer still. The planet's natural clock is still running, but its rhythm changes so slowly that no human lifetime can perceive it directly. The moon is therefore more than a bright object in the sky. Its gravity has reached into Earth's rotation itself, changing the rhythm of day and night over time. Every day we experience now carries the result of a relationship that began when the two bodies were far closer together. And the clearest sign of that gravitational pull still appears each day along the world's coastlines. The clearest effect of the moon's gravitational pull still appears every day along the world's coastlines. Water rises, covering stretches of sand and the bases of rocks. A few hours later, it retreats, leaving behind a band of wet shore, small tide pools, and traces of seaweed. Then the water returns. The movement is so slow, familiar, and regular that it is easy to think of it as a natural rhythm that has always existed. But behind the rise and fall of the sea is gravity, connecting Earth and the moon. Tides are produced mainly by the moon's gravitational pull, together with the influence of the sunday. The sun is vastly more massive, but the moon is much closer to Earth, so the difference in gravitational pull across different parts of the planet is more pronounced. It is this difference, rather than gravity alone, that stretches the oceans into regions of higher water. The side of Earth facing the moon is slightly closer to the satellite, and therefore feels a somewhat stronger pull. Water in this region tends to rise toward the moon, but tides do not appear on only one side. On the opposite side of Earth, another tidal bulge forms because Earth itself and its oceans do not respond in exactly the same way to the moon's gravity. One way to picture this is to imagine the entire Earth moving together with the moon around a shared point of balance. The side of the planet nearer the moon is pulled more strongly, while the far side is pulled more weakly. This difference gently stretches the layer of ocean water along the line connecting the two bodies, producing two bulges on opposite sides of Earth. This is only the simplest picture. The real oceans do not cover Earth as a perfectly even, freely moving layer of water. Continents interrupt the flow, the seafloor varies in depth, and bays, straits, and curved coastlines force the water to move in different ways. For this reason, the timing and height of tides vary greatly from place to place. Some coastlines experience only small changes in water level. In other regions, the sea may rise and fall across a much greater range. As Earth rotates, coastlines move in and out of the regions of higher and lower water. That is why many places experience 2 high tides and 2 low tides during a tidal day. This cycle does not line up exactly with the 24-hour day because, while Earth is rotating, the Moon is also continuing along its orbit. Earth must turn a little farther before the same location faces the Moon again. As a result, high tide usually arrives later from one day to the next. People who live near the sea may notice that the tide does not return at exactly the same hour each day. It shifts gradually with the position of the Moon, like a natural clock governed by the rhythm of 2 celestial bodies rather than by Earth's rotation alone. The Sun also contributes to the tidal rhythm. When the Sun, Earth, and Moon are nearly aligned, the gravitational effects of the Sun and Moon reinforce one another. The difference between high and low tide is then usually greater. This commonly occurs around the new moon and the full moon, when the Sun and Moon lie in directions that are nearly at right angles as seen from Earth. Their effects partly oppose one another. Tides are then generally weaker, with high tides that do not rise as far and low tides that do not fall as much. This pattern repeats with the Moon's cycle, although the shape of the coastline and the seafloor still determine how it appears in each location. On a gently sloping beach, the retreating tide may expose a broad stretch of sand. Small organisms hidden in rocky hollows and muddy areas wait for the water to return. In a narrow bay, currents may become strong as the tide changes direction. In an estuary, rising seawater can also influence the flow of fresh water arriving from inland. These different scenes all begin with the same gravitational force, but local geography transforms that force into its own particular rhythm. Tides do more than raise and lower the surface of the sea. Enormous masses of water move through ocean basins, rubbing against the seafloor and the edges of continents. That motion removes a small amount of Earth's rotational energy and converts it into heat. This is the tidal friction that has gradually lengthened the day and helped move the Moon into a wider orbit. A rising tide along a coastline is therefore not separate from the long history of the Earth-Moon system. It is the continuing expression of the same process that began when the 2 bodies were much closer together. Each movement of the water involves a tiny exchange of energy. Every individual exchange is almost insignificant, but over immense spans of time, they change both the Moon's distance and Earth's rotation rate. When the Moon was closer, tidal forces may have been far stronger. The early oceans, once they had become stable enough to exist, would have experienced greater deformation than they do today. As the Moon moved farther away, that influence weakened. The present rhythm of rising and falling water is therefore also the result of a system that has been changing for billions of years. Although the Moon plays the largest role, tides do not always follow a simple pattern. In some regions, tidal waves travel around entire ocean basins. They meet continents, change direction, overlap, or slow down. As a result, some locations experience only one clearly defined high tide each day, while others have 2 high tides of unequal height. This is why predicting tides requires more than knowing the Moon's position. Calculations must also include the Sun, the depth of the sea, the shape of the coastline, the direction of currents, and a history of local observations. Gravity establishes the basic rhythm, while the oceans and continents determine how that rhythm is expressed. For life along the coast, tides create a special transition zone between land and water. At some times, the area is completely submerged. At others, it is exposed to the air. Organisms living there must adapt to both conditions. They cling tightly to rocks, retain water within their bodies, or hide inside small crevices when the tide goes out. The rhythm of the Moon has therefore become part of the rhythm of life in many coastal ecosystems. Tides also help mix water, transport nutrients, and connect the open sea with estuaries. Although they are not the only cause of these movements, the Moon's gravity helps maintain an ocean that is never completely still. Water is continually shifted from one place to another through overlapping cycles of different sizes. If we look at a beach for only a moment, the change seems very slow. But over several hours, the waterline may move a clearly visible distance. Over billions of years, the same gravitational pull has also slowed Earth's rotation and moved the Moon farther away. An ordinary coastal event therefore contains both the present motion of the oceans and the long history of two worlds. The Moon never touches the surface of the sea directly. Hundreds of thousands of kilometers of space separate it from the oceans. Yet, gravity crosses that distance and causes an immense layer of water to change both its shape and motion. Wet sand, tide pools left among the rocks, and the retreating waterline are all visible traces of that invisible connection. A body born from collision became the force that helps regulate the breathing rhythm of the oceans. A body born from collision became the force that helps regulate the breathing rhythm of the oceans. But the Moon's influence is not visible only in the rising and falling of the tides. Over immense spans of time, its gravity has also affected the way Earth maintains the orientation of its rotation in space. Earth does not rotate with its axis perfectly upright relative to its orbit around the Sunday. The planet's rotational axis is tilted by about 23.5 degrees. Earth can be imagined as a slightly leaning spinning top traveling around the Sunday. That tilt changes the amount of sunlight received by each hemisphere throughout the year and helps create the seasons. When the northern hemisphere tilts toward the sun, it receives more direct sunlight and experiences longer daylight hours. Summer arrives in the north while the southern hemisphere passes through winter. Half a year later, the positions are reversed. It is the tilt of Earth's axis, rather than changes in its distance from the sun, that primarily creates the familiar rhythm of the seasons. That tilted axis does not remain perfectly still. Earth is influenced by the gravity of the sun, the moon, and the other planets. Small forces acting over a long enough period can alter both the direction of the axis and the degree of its tilt. The rotational axis also moves slowly in a circular pattern, much like the axis of a spinning top beginning to wobble. This process unfolds over thousands of years and contributes to natural changes in Earth's climate. The Moon does not hold Earth's axis completely motionless, but its gravity may help limit changes that would otherwise become much larger. Because the Moon is relatively large compared with Earth and lies fairly close to it, the satellite has a significant influence on the planet's rotation. Its presence helps keep Earth's axial tilt varying within a comparatively stable range over long periods. This does not mean that Earth's climate has always been stable. Our planet has still experienced ice ages, periods of warming, shifts in ocean circulation, moving continents, and many other major changes. The axial tilt is not fixed precisely at 23.5 degrees either. It changes slowly in cycles, increasing or reducing the amount of sunlight reaching high latitudes and contributing to changes in climate. The Moon's role is to help make those variations less extreme. Without this large satellite, gravitational influences from the other planets might cause Earth's axis to behave in a more complicated way. The tilt could pass through a wider range of values, causing the distribution of sunlight across the surface to change more dramatically over time. A major change in axial tilt would make the seasons very different. If the tilt increased greatly, summers in some regions could receive far more intense sunlight, while winters became darker and colder. If the tilt decreased significantly, the differences between seasons could weaken. Long-lasting changes of this kind would affect polar ice, rainfall, atmospheric circulation, and the way heat is transported around the planet. Even so, we should not conclude that Earth would certainly have been unable to support life without the Moon. Life depends on many factors, including distance from the sun, liquid water, the atmosphere, chemical composition, geological activity, and the planet's long history. A world without a large moon could still maintain suitable conditions under certain circumstances. A more careful way to describe the Moon's role is to say that it may have helped Earth maintain a more predictable climatic rhythm over long periods. The relative stability of the rotational axis does not prevent all change, but it may reduce the likelihood of extreme variations caused by shifts in axial tilt. This could have provided a steadier foundation for the oceans, atmosphere, and life to develop together across billions of years. The exact strength of this influence remains a subject of research. Different models can produce different results depending on Earth's initial condition, its rotation rate, the positions of the planets, and the way gravitational forces interact. Some studies suggest that even without the Moon, Earth's axis might remain stable for certain periods. Other models indicate that the variations could become significantly stronger. These differences remind us that climate history is not controlled by a single factor. The Moon is one part of a larger system, not a switch that determines everything. It influences the tides, Earth's rotation rate, and the direction of its axis. But those effects always interact with the Sun, the oceans, the atmosphere, and the planet's internal structure. What is remarkable is that this role was not predetermined from the beginning. The Moon itself was the result of a violent event. Material that had once been heated and thrown away from Earth gathered into a new celestial body. That body then began influencing the very planet that helped create it. During the earliest stages, when the Moon was closer, its gravitational influence was also stronger. Over time, the satellite moved farther away, Earth's rotation slowed, and the relationship between the two bodies changed. Even so, the Moon remains close enough to produce clear tides and to contribute to the long-term stability of Earth's rotational orientation. Viewed from one day to the next, this influence is almost invisible. Earth's axis does not noticeably change direction before our eyes. The climate does not shift into an entirely different state after a single rotation. But across millions of years, small gravitational forces can shape the way seasons change and the way solar energy is distributed over the surface. A rising tide along a coastline and a planetary axis tilted in space may seem like two completely different phenomena. In reality, both are connected to the same gravitational force. In the oceans, that force moves water over a period of hours. In Earth's rotational axis, its influence becomes clear only when viewed across very long spans of time. The Moon therefore affects both the rhythms closest to everyday life and the much larger motions of the planet. It helps create the tidal cycles that coastal organisms experience each day, while also helping Earth's rotational orientation avoid more extreme changes over its long history. We cannot know exactly what kind of world Earth would have become if the ancient collision had never created the Moon. The planet might still have had oceans, an atmosphere, and seasons of its own. But the history of its rotation, tides, and climate would probably have followed a different path. The Moon does not guarantee life, but it may have helped create a more stable environment in which life had time to develop. The Moon is therefore more than the result of a collision. It is also part of the reason Earth became the familiar planet we know today. The Moon has remained beside Earth for nearly the entire history of our planet. It raises and lowers the oceans, has gradually slowed Earth's rotation, and may have helped keep the planet's axial tilt more stable. Yet when we trace this relationship back to the moment it began, we still find a case file with many missing pages. The giant impact hypothesis explains most of the larger picture. About 4.5 billion years ago, the young Earth may have collided with a planetary embryo commonly known as Theia. The heat and energy released by that event melted rock, launched an enormous amount of material into orbit, and opened the way for the Moon to form. But the details that would define exactly what happened remain uncertain. How large was the impactor? Was it roughly the size of Mars, as traditional models suggest? Or were the two bodies once closer in mass? Did it form beside Earth from similar sources of material, or did it arrive from another region of the young solar system? Was the collision nearly head-on, a glancing impact at an angle, or something more complicated than the simple images often used to describe it? Every answer changes the rest of the story. Size and speed determine how much material is thrown outward. The angle of approach influences which rock merges into Earth and which enters orbit. Earth's rotation before the collision may determine how much of the material that formed the moon came from our own planet. Even a small change in the initial conditions can produce an entirely different system. There is also no single answer for how long the moon took to form. Traditional models suggest that material left after the impact remained in a hot disk, where it gradually collided and accumulated over many months or years. More recent high-resolution simulations suggest that a large satellite might have appeared within the first few hours. Perhaps a main body formed very quickly and then continued gathering rock and dust from the surrounding debris. These two possibilities may represent different stages of the same process. Lunar rocks have not produced a completely unified timeline either. Some zircon grains in Apollo 17 samples indicate that the moon already existed at least around 4.46 billion years ago. Those crystals could form only after some of the molten material had cooled enough to crystallize. The impact and the moon's appearance must therefore have occurred earlier, or not much later than that recorded date. Other rock samples, however, preserve evidence of events around 4.35 billion years ago. This difference does not necessarily mean that one group of samples is correct and the other is wrong. Rocks do not always record the same event. One mineral grain may preserve the age of its original crystallization, while another sample reflects a later period when the crust was heated, melted, or remade. The young moon was still very close to Earth, where tidal forces were much stronger than they are today. Its interior remained hot, its surface was repeatedly struck, and its first crust had not yet become fully stable. A major thermal event may have reset many of the natural clocks within lunar rocks around 4.35 billion years ago. In that case, the younger age would not record the moon's birth, but a time when the body was profoundly transformed after it had already formed. This is why the age of a world cannot be reduced to a single number. Each rock sample is like a witness standing in a different place. A zircon grain speaks of the time when magma began to cool. Rocks from the bright crust preserve the stage when the first surface appeared. Samples altered by impacts add records of later events. Only when these accounts are placed beside one another does the timeline gradually become clearer. But the collection of rocks currently available does not represent the entire moon. The Apollo and Luna missions returned priceless samples, yet most of them came from a limited number of locations on the near side. The far side, the polar regions, ancient highlands, and many deep basins have never been sampled directly. Each region may have experienced its own history of heating and impact. A single rock from a previously unexplored region could change the accepted age of the crust. Material from deep beneath an impact basin could reveal the composition of the mantle. Rocks from the far side might help explain why the moon's two hemispheres are so different. Material from the polar regions could reveal how water and other volatile substances arrived, escaped, or remained preserved. Future missions will therefore do more than continue mapping the terrain. They may recover missing parts of the record. New seismometers could provide a clearer view of the moon's deep structure. More precise gravitational measurements may reveal the thickness of the crust and the size of the core. Laboratories on Earth will continue studying ever smaller mineral grains with a degree of precision that earlier generations did not possess. Isotopic analysis may also identify extremely subtle differences between Earth and the Moon. Those tiny deviations could be surviving traces of the lost impactor, helping reveal where it formed and how much material it contributed. They could also show how thoroughly the collision mixed the two worlds before the Moon solidified. At the same time, supercomputers will continue testing new scenarios. Improved simulations may follow in greater detail how rock melted, vaporized, mixed, and gathered into a satellite. But no matter how powerful the calculations become, a computer can show only what might have happened. A scenario becomes credible only when its result matches the real moon's mass, orbit, structure, and composition. The story of the moon's origin will therefore continue to be revised as new evidence appears. This does not weaken science. On the contrary, An explanation has value only when it is willing to change in response to what rocks, minerals, and the motions of celestial bodies actually reveal. Every unanswered question is not an empty gap, but a place where the next investigation can begin. At the end of this journey, we can return to the small rock that opened the story. Its outer appearance does not reveal that a planet was once struck. It is no longer hot, it does not glow, and it does not resemble the debris disk that once surrounded Earth. Yet inside it, minerals still preserve age, isotopes still preserve origin, and the structure of the rock still records episodes of melting and cooling. That rock cannot tell us by itself how large Theia was or where it came from. It cannot confirm whether the moon formed in a few hours or over many years, but it can eliminate answers that do not fit, while reminding us that matter can preserve the past far longer than any living memory. A small rock does not close the case. It opens a doorway through which humanity can look into a time when Earth had not yet taken on its familiar form. Through that doorway we see a planet heated and remade, another world disappearing, and a new satellite emerging from the material left behind. The meaning of this story does not lie in turning a catastrophe into something good. The universe did not arrange the collision with the intention of creating the moon. There were only matter, motion, and gravity continuing to act after the event. Yet from that chaos, a new order emerged and endured for billions of years. The moon did not erase the evidence of the impact. It is part of that evidence, transformed into a new shape. Its presence shows that one event can end a world while beginning an entirely different relationship. Not every loss creates something new, but in planetary history, formation and destruction often lie closer together than we imagine. The consequences of the collision have not disappeared. They are present in the rising and falling of the oceans, in the 2-4-hour day, in Earth's gradually slowing rotation, and in the increasing distance between the two bodies. The past does not remain only inside rocks. It continues moving through the present world. From an event that may have melted a large part of Earth, the moon was born, and afterward, it did not immediately leave. It remained, pulling the oceans, gradually lengthening the day, helping regulate the planet's axial rhythm, and quietly carrying the memory of the moment when Earth was reshaped by the universe. The moon is therefore more than an object orbiting Earth. It is the open record of a vanished world, a collision not yet fully understood, and a past that still quietly lives within the rhythms of our planet.